So welcome to this event organized by the association Together. So Together, as the name implies, brings people together from different nationalities. And I think we have quite a few nationalities here tonight. We have Chinese, we have Korean, we have Congolese, we have Hungarian, we have Romanian, we have Dutch, we have Japanese, we have Philippines, we have India, New Zealand, and Republic Czech, France, Canada, Russia. Yeah, okay, so very international group. And tonight we're privileged to have Victor as our conference speaker. So I'm going to read an introduction to him. So Victor is married to Naomi, who is French. So is Victor, as a matter of fact, from Chinese parents, born and raised in France. They have two little boys. He did what they call a grande école in France, a very good engineering school in Paris on theoretical and applied optics, and then a PhD thesis on crystalline mirrors for space-time meteorology and application on gravitational detectors. I don't know what that means. Then he did postdoctoral work on commissioning of the detection system of gravitational wave detector and on the modeling of optical layout for future improvement of the detector. So the only thing I know about black holes is what I read on internet the other day. It said, if a black hole invites you to come for a visit, decline the invitation. That's the extent of my knowledge. So Victor, thank you very much for coming. So he's going to talk for about an hour and or less. Mm-hmm. And then there will be time for questions and interaction. So thank you very much. And after, yes, we'll have some lunch and some drinks. Yeah.
Okay. Good evening, everyone. Thank you for coming. It's very encouraging for me. And I'm very happy and honored to share with you about this subject on black holes, which is a very large and complicated topic, and I will try to explain and make it understandable for you. So when we talk with black holes, we have first to have a definition of it. So here it is. And by the way, for this conference, there will be two parts. So a first part more about the technical aspect, the scientific aspect of black holes. And then there will be a second part, more of reflection on philosophical, metaphysical aspects. So how are these massive objects can point to maybe something or someone greater and bigger. So you will see. So definition of a black hole. So a black hole is an astrophysical object which is so compact that its gravity attracts everything and prevents everything around it to escape, even light. So that's why we call it a black hole, because it's black, the light cannot escape from it, so it's black by definition. So there's a lot of words and keywords here, and one of the main keywords that we are going to explore a bit is gravity. What is gravity? How come that planets, objects in the universe has gravity? Like if I jump like that and I will come back to the ground, what makes that? What is gravity? So to understand gravity, we have to talk about one guy. Maybe you know him. He's kind of a bit famous in modern physics. He's called Albert Einstein. So he's a monument in modern physics. And he published his famous paper in 1915 on the theory of general relativity. So it's a very complex theory, but simply put, it said that there are matter can be described by 4 dimensions. So 3 dimensions of space, we can see that 3D, so there's 3 dimensions of space, and then 1 dimension of time. And so one of the implications of his theory is that space and time are linked together. So there's something that is linking space and time. And so here is, I just put there for the beauty of it, it's the equation. There will be the only equation here for tonight about the general relativity. So I'm not sure I will be able to explain all the terms, but it's very beautiful to see that. So there is a link between time and space. So it's called the space-time continuum. So it says, so the implication of the general theory of relativity of Einstein is to say that every object, everything that has a mass, will have an influence on the environment around him. Will deform the space around him, and so all objects that are coming near something that has matter will be influenced. So the matter that is on the Earth, or inside you, or in this table, all that has an impact on the environment around, and so it will deform what we call the space-time continuum. So this is what we see in this image. You see the sun, its mass will deform the space around it. So when the Earth approaches the sun, it will be attracted to it because it will follow this deformation. And so we talked about Albert Einstein. We have to talk about another guy, which name is Karl Schwarzschild. So he solved the equation of Einstein, of general relativity. And by the way, he did that while he was dying of skin disease during World War I, and he was fighting the Russian soldiers. So it's not bad. he was able to solve Einstein's equation. And basically, from these equations, he showed that the existence of an object that is so compact, it can literally tear the space-time continuum, it can create a hole. This kind of object can exist, and these objects are called black hole. So it's black because the light cannot escape, since the gravity is so intense, so even the light cannot escape. And it's a hole because it's so dense that it will create a hole inside the space-time, represented by this piece of cloth. And so mathematically speaking, what are black holes? How can a black hole be created? Mathematically speaking, if you compact an object, if you are able to squeeze an object like the Earth, for example, into the size of a peanut, poof, you create a black hole. So black holes are just objects that are very, very, very dense and very compact. And if, for example, you take your car and you can squeeze your car into the size of a dust sand, it becomes a black hole. So black holes are basically objects, mathematically speaking, that are very compact, and so compact that they will be really have a really strong gravity. So this is what black holes are. And so how do they look like? Well, it's hard to say because by definition we cannot see a black hole, because if you want to see an object, you have to see a light reflected by an object. I can see you because you are reflecting the light coming from above. So you're literally shining the light of this room. But if there is no light coming from an object, you cannot see it. So that's why it's black. What we can see is the influence, the impact a black hole has on its environment. So since it has this big gravity, it will deform the space around it, and we will be able to see this deformation. So we can see that, for example, this is a picture. So it's interesting to see that around we see where the red arrow is pointing, it's galaxies. but a galaxy is so deformed by the gravity of the black hole that it's almost like you're seeing through a ball lens, a lens that is the shape of a ball, of a big sphere, and you see the deformation of all what you see. And the light, it's not the light coming from the black hole because there's no light, but it's actually a sun which is behind the black hole. So if you imagine if my fist is a black hole and we have a sun here, you will be able to see the sun which is behind it because the light of the sun will be deflected by the gravity of the black hole and will come directly to your eye. So what you see is literally what's behind the black hole. So you see it's almost like a lens that's showing you all what is around. So let's get a closer look to what's inside the black hole. What's inside of it? At the center of it, there is what we call a singularity. So it's a point, no volume, no surface, and the density of this point is going toward infinity. And the time is stopped at this point. So it's hard to imagine, but mathematically, this is coherent with Einstein theory. And so around this singularity, the space-time is deformed. And so deformed that nothing can come out of this space. And then we have what we call the event horizon. So it's a boundary, it's not a physical boundary, but it's a place around this deformed space-time. And all objects that had gone through this event horizon will the only direction they will go is toward the center, toward the singularity. So if you take a planet, if you take a horse, if you take your car, or if you take Matthew McConaughey, which is the actor of the movie Interstellar, well, if they go through this event horizon, they will go inside the black hole, and there will be no other way. They will be attracted to the center. So there's a lot of mystery around black holes. There's still a lot of research around it. We do not know how it's kind of overwhelming. It's to know that time and space are so deformed that the way time is passing around the black hole is like something that it's hard to understand. And there's a lot of mysteries, and so that's why we just try to study them. And one of the difficulties has been raised by another physicist that is also well known, who is called Stephen Hawking. So he studied quantum physics, he studied cosmology, so it's very complex areas of modern physics. And he studied matter and antimatter. So there's matter, there's antimatter. So just admit that exists. And matter and antimatter, they are separated around the black hole. They can be separated. So in red, the red arrows represent the matter, which is coming out from the black hole, and antimatter is coming inside. So this is what he calculated. This is what Hawking calculated. So this is what he concluded. He concluded that matter, is going out from a black hole. So the black hole will eventually evaporate. It will radiate matter and it will disappear. And that's problematic. That means that there are objects coming inside a black hole. So they are matter coming inside the black hole. And the black hole, because of this radiation that Hawking discovered, is evaporating matter also, so it will disappear. So the big question is, where goes the matter? Where goes the horse, the actor, the car? Because of it's evaporated. And this is a paradox, and we don't like paradox in science. And this is something that is not predicted by physics. Quantum physics, for example, says that if matter is appearing in a certain form, we should be able to recuperate it, to retrieve it. So if example, if I burn a book, from the ashes, from the atoms and the ashes of this book, I can give and can have the information back. I can know if this book was a philosophical book, a Harry Potter book, or etc. But if matter disappears like that, this is a problem. Then where goes the information? That's the main question. So this is just to make you feel that there's a lot of mystery around black holes, so we need to be able to study them. So how do we do that? Well, we try to detect them. And how do we detect them? Well, we detect signals that can come from black holes. And this is what we call gravitational waves. And this is the field of study of my PhD thesis and my research work. So what are gravitational waves? To understand, you have to admit that sometimes in the universe, black holes can merge. So there are two black holes can come closer together, like two lovers that are meeting together, and then they will revolve around each other. They will enter in sort of a dance. It's kind of romantic. They will come into a dance, and then the closer they get, the faster they will turn, and then at some point they will meet and they will merge. And from that merge, there will be a wave of gravity that will be generated. So I think I have a video. I don't know if it was work. Yeah. So you see, there are these two balls which represent the two black holes. They are being attracted to each other due to their gravity, and so they are provoking these waves. They are coming together, and bam! And here is the gravitational wave that will then be spread into the galaxy, into the universe. And so, what is a wave? So, a wave is a signal. To make you understand, so we have waves in around you. Light is a wave. We have waves in the sea. So, wave is a signal having ups and downs, regular ups and downs, maximum and minimum, and it transports information. So, light will transport information. The sound also, what you hear from my voice, it makes the molecules of air vibrating, and it will go into your ear, and then it will transform in electro signals, and then you will be able to interpret it. And so we have also waves of gravity, which is acting on the gravity, it's acting on space-time, which transports information coming from the black holes, fusion. And so by detecting these types of waves, we are able to detect and to study and to understand better black holes. So we are trying to detect the signals, these signals coming from black hole, like trying to listen to a symphony of music coming from a music play. And so to do that, we need to use detectors. This is the main challenge. The detection of gravitational wave is sometimes a recent research field, because the problem is that these waves' amplitude is very weak, because black holes the distance is enormous. Black holes come from very far, so the furthest these signals will travel, the weakest it becomes. And so in 1915, to give you the dates, in 1915, Einstein's general theory predicted existence of black holes and of gravitational waves also. But we had to wait until only 2015, so 100 years later, to be able to have the first detection of these waves coming from black hole fusion. Because we needed to have enough sensitive and precise instruments to be able to detect them. So how do we detect? So we cannot detect directly these signals. We have to detect their impact, because these signals are very low. We have to come up with a solution that's enough, that can be enough sensitive to be able to detect. And yeah, in 2017, there was a Nobel Prize that has been won following the detection of gravitational wave signals. So we see that these waves are deforming space-time. So they are deforming, namely, the distance between objects. Because if you remember the piece of cloth, we see if an object is in the center and is having this weight, so the trajectory will be deformed, so the distance between the objects will be also impacted. So we need that. We need to see how to come up with a system that is able to measure this distance modification due to the passage of a gravitational wave. And the real problem is that they are very weak. So this deformation. How weak? Well, at 10 to the minus 22. So for scientists, you know this kind of, but to make you a bit understand, it's like you try to see if an atom move at the distance of the sun. So you take one hair, an atom is 1 million times smaller than one of your hair. You put it at the distance of the sun and you try to see, oh, did it move? It's impossible. You cannot just have a very good telescope. You need to have an extremely precise instrument. So how do we do that? Well, we use what we call interferometry. If you've studied a bit optics, it's a very precise technique. So it's rather simple. You take a laser, which is represented by the red dot. So a laser is a specific type of light. It's very focused and has very specific properties. And so you split it into two beams, one beam coming toward one mirror and another beam coming toward a second mirror. And you place the mirrors like that. And so the beams will be reflected by the mirror and they will interfere then, and then we detect the light. So the interference on these two beams, depending on how the two beams are matching, there will be fluctuation into the interference. So if the beams are perfectly matched, the light is at its maximum amplitude. If the beams are not perfectly matched, well, it will cancel the light. So how do you use that to detect? Well, imagine that you have a gravitational wave coming through this instrument. It will deform the distance of propagation of the light. So it will deform the distance between the distance between the laser and the mirror on one side and on the other side. And so the light that you detect will fluctuate because of the influence of the passage of a gravitational wave. So I have another video that helps us to understand a bit better. I don't know if maybe it doesn't work. I will see if here. So we have the light which is going through the splitter and toward the mirrors. So you see it's this wave, the light from the laser. It's going toward the mirror, it's being reflected. And you see when they interfere, we will see the ups of the waves and the down of the waves that will mix together. And when a gravitational wave goes through this system, it will make slightly move the mirror. And so the beam also, the distance will be impacted. And we see here the light that will fluctuate. So if we detect this kind of fluctuation, we might guess that a gravitational wave has passed this, and we can analyze the fluctuation, and we are able to have information on this gravitational wave. So it's kind of an elegant way and very precise way to to detect. But of course, things are not that easy. You cannot just put one laser on a table and 2 mirrors, and that's all. Things in reality are much more complex than that because of the weakness of these signals. So in reality, how does it work? Well, the mirrors that you have is not the mirror that you have in your bathroom, of course. It's extremely flat and clean mirrors. They are the most flat mirrors of the whole world. Their surface is absolutely homogeneous, and they are made in France. They are made in Lyon. So they weigh 40 kilograms about, and then we don't just project lasers in the air because there are dust in the air. There are fluctuation in the air. So we had to inject the laser in the void. And the longer the beam is going, the more precise it is. So we have instruments that are this size. So what you see here, the 2 arms, they are 3 kilometers long. So at the very end, we have the mirrors, and the laser is here. So this is to increase the precision. So it's one of the most precise experiments in the whole world, scientific experiment. And then it's not over, because one of the main research on this type of experiment is to try to identify and to mitigate what we call noises, because there are lots of noises that will interfere with our detection. And maybe if you're working in ETL, you have this type of study also. For example, if someone is walking around the mirror, just the vibration of his step on the ground will interfere with the detection. And it's like, if you try to imagine, it's like if you were in a giant mall, in a giant mall, and there's a lot of noise, babbling, etc. And you try to listen to my voice, and I'm trying to speak to you like that. And you have all the kids are shouting, and that's impossible. So you will need to lower all the noises so that you'll be able to only focus on one sound. And so we have a lot of noises. We have the noise linked to the detection. We have the noise linked to the laser. So the laser fluctuation by itself will have interference. The noise linked to temperature also of the mirrors. The seismic noise. So if there's an earthquake anywhere on the planet, the detector will be able to detect it. So all this we are searching, and we are trying to identify and trying to find solutions to mitigate these noises, in order that in the end there's only the signal coming from the gravitational wave that we are able to detect. And this is a big part, and it's not easy. And sometimes when we are trying to commission the detector, trying to set it, we have noises that appear. We don't know where do they come from. I remember one time I was working on the detector, and we found like a noise, and we did not know where it did come from, and it lasted several weeks, and then it disappeared. And then we think it's a hypothesis, but there was a rat that came into one of the instruments and died between the wires. And we think that it's because of that, that it made this kind of noise appear in the spectrum, and took several weeks to identify this type of fluctuation of noise. So, on the Earth, there are several kind of these detectors. There are 2 in the United States. In Europe, there's one in Germany, which is more experimental to start to launch. And then there's Virgo. I worked on Virgo, which is in Italy. There's one in Japan, and there's one planned in India also. And this is important because when we want to see signals coming from space, we need to localize them. So with several detectors spread into the whole world, we are able to do triangulation and to be able to detect and see the direction from where it comes from. So some results, very, very, very fast. If you're interested, I put some articles. So there has been 4 observation campaigns. So once every noise is identified, we can mitigate enough. We like switch on the detector, and then we are having an observation mode. So there are a lot of time of commissioning. So trying to, and then we switch on the detector. And so there has been 4 campaign of observation, and the last one lasted 2 years, and it helped to detect a lot of signals, more than 200 jet gravitational wave signals. And so there are some results, not only about the black holes, but we were also able to confirm some theory, some astrophysics theory on Stephen Hawking's theory or Einstein general relativity, have a more accurate appreciation of his theory. So you see that the field of study is not only concerning black holes, but it's concerning the whole field of astrophysics, of cosmology. So we can make a little pause because this is the first part. And if until now you have some questions, maybe we can take 10 minutes. And if you have any question, you can ask. Or if you have things that you have not understood, please feel free. And then there will be the second part.
Question.
Yes.
With all the things that they've done, they spend money, spend millions of dollars. I don't know how much.
Yeah.
What's the benefit of that for mankind?
Yeah, that's a good question, and it's often a question that we ask for fundamental physics experiments. So, yeah, this is fundamental research. So it has not a direct impact on your everyday, on mankind every day. So it's firstly about making science and progress. But today, I think we have more and more this kind of big experiment, which and people are. It's not only research, but they were also engineers, and the project had to make partnership with companies, engineering companies, and engineering companies. They have they can have some application in the civil in our world. So there are some companies that are working inside. So engineering companies working with the researcher, and these companies then using what they learn will then be able to develop products that will be more for the large public. So that's how I'm understanding it. Yeah. Yes, and then?
So the only source of the gravitational waves is the 2 black holes. So
Yes.
how can you be sure that there is no other sources, so that waves that you detect are coming from the black holes?
Yeah. I mentioned black hole fusion, which is the main event, but there are also indeed there's also neutron star, and also there can be black hole and neutron star fusion together, and also supernovas. So and this is all the expertise of astrophysicians and cosmologists. So when we detect the signals, we detect, it depends, we have a frequency of the signal, we will have the fluctuation, we will have the amplitude, and based on this information and with the theory of cosmology, we will be able to say if it's a black hole, if it's a neutron star, if it's other. So it will mainly rely on the different information that we will extract from the fluctuation of the light that I showed you in the video. Yeah, and so we can, for example, we can extract the size of the black hole, the direction, because the black hole can have a specific direction, the mass of the black hole, we'd say, etc. Yes. Yeah.
If I make two questions.
Yeah.
Okay. So you say there is a 3 or 4 sensor actually running around the world.
Yep.
And you guys are observing like 360.
Yeah.
Does those sensor are sharing information for say, for example, someone hears something, you can ask another sensor, have you heard that as well? So are you guys communicating on information you get? And just one question. So you were saying like to create a black hole, we take something big and we make it pretty small.
Yeah.
Does that mean like the smaller a black hole is, the strongest, the more powerful it is, or there is nothing to?
Yeah. So for the first question, yes. So there are several detectors, and yes, it does communicate to each other. When the detectors are switched on, usually they run together, and so when there are detection from one detector, they will then inform the others, so that the others will try to look at the good direction and then try to give more precision about where it comes from. So yeah, there is a worldwide collaboration between the different detectors, and then mathematically I said that if you compact an object, it will become a black hole. But in reality, how a black hole formed, it's with the stars, the explosion of a stars. When the stars come to the end, it will die, and so there is a process where the stars the gas will come out from the star, and then its heart will collapse due to the gravity. And when there's a very big star, so indeed the collapsing and the gravity is stronger. So and then this will create a black hole. So in reality, in the universe, it's the death of a star which will then give birth to a black hole. So and we need a star that is massive enough to have the good gravity to be able to give a black hole. But yeah, there is a link with the more the higher the gravity, the more it will be compacted, and then the stronger the black hole will be. Yeah.
I have maybe 3. First will be with respect to the, as you said, amplitude is 10 raised to minus 10, but in hertz, can you tell how it is? Hertz.
Sorry, can you?
Hertz frequency.
In hertz in frequency. I have to remember that. Because I'm not sure about the amplitude of hertz. So there's a lot of I think it's between 10 and 10,000 hertz. So the spectrum, So if I remember correctly,
Our galaxy is known to us. How many black holes are there right now?
Known to us, Well, you see, we have 200 gravitational waves, so I think most of them comes from black hole fusion. So given the size of the universe, there can be a lot. So known black holes, we have a few hundred since the beginning of the detection, but it can be more because there are lots of signals that we miss because sometimes the detector does not work, or we have to pause to do some repairing, etc. So, yeah.
And the third part is after the environment, like usually we know what we studied, that after certain kilometers from the Earth,
Mm-hmm.
there is total vacuum.
Yeah.
If there is vacuum, so how we are catching up the sound?
Oh yeah, so it's not sound. The signals it's the deformation of the space-time. So it's not a wave of sound. It's a wave of gravity. It's hard to to conceptualize.
It's in terms of light or sound.
Yeah. So you can imagine like as this thing when the waves pass, it's like it's stretching and contracting the space. Yeah, so it's like if the waves pass in this room, the distance between you and me will be stretched and then contracted, and yet we will not move. So you see, that's the general theory of Einstein. So it's like if you have, for example, I think this is the image. You can say on the balloon, you put 2 points on the balloon, and when you blow the balloon, the 2 points will stretch, but it will stay at the same place. And this is a way that we can imagine the space-time. So the gravitational wave will act on the distance between the objects, and so it will act for the distance between mirrors, for example, on Earth. And then from that we can detect them. Yeah.
Thank you.
Yeah. Yeah.
Are gravitational waves the only way to detect a black hole? Are there other means to detect it?
Yeah, there are other ways. Of course, yeah, using direct observation. So not of the black holes, but of the environment of a black hole. Yes. So, and I think that some years ago we had a photography of a black hole using a specific technique with using telescope. So we were able to have a snapshot, a photography of a black hole. But yeah, we can do it by direct observation of the environment. We know that in certain area of the universe there is a black hole, and we see the stars that are around that are influenced by the black hole, and we can have some information. And yeah. Yes.
You talked about I can't remember the exact term, an event
Horizon, yeah.
Event horizon. How? What's the diameter of that? Just so I know how far to stay away from
It depends on the size of the black hole. So black hole can have different sizes, and it can be millions of light years. So I will talk a bit about the distance we have in the universe. So it can be huge, yeah. But the universe is even bigger. So normally we are safe. There's a black hole. We think there's a black hole in the center of our galaxy, but our galaxy is 100 million light years. I will give an idea of it, but it's huge. So we are safe. We can wait until we go close to the black hole. So. Yes.
And when an object comes into the black hole,
yeah.
The black hole increase, the gravity of the black hole increase or not?
So normally, yeah, the size of the black hole will increase because the matter going inside will increase, yeah. So yeah. And the paradox is that the black hole, according to Hawking, it's also evaporating, so it's a bit weird, yeah. Yes?
I want to ask that how machines you mentioned that detects the gravity waves.
Yeah.
How is it more precise if the mirrors are very far away from the laser?
Yeah, that's an interesting question. So this is using the properties of the laser and also the properties of when you place a laser in a mirror, depending on the distance, you will be able to make the light resonate inside what we call a cavity between the laser and the mirror. And the longer is this cavity, if there's a little difference, between when if the laser is moving or if the mirror is moving, well, the longer the distance is traveled by the laser, the more precise it is. Because if you just travel like a bit, then if it moves, you will not be able. But if you travel like a kilometer and then comes back, depending on how you position the two, you will be able to have a greater precision. So this is the properties of a laser, because it's a light that is very focused, and so you're able to make it resonate, and then by resonating inside the cavity between the mirror and the laser, you'll be able to have more precision on the laser. So there's another question. Yeah, Kata.
So I have this following question that he said, why it is only 3 kilometers or it is like lab.
Yeah. So the longer it gets, the better it is. But then we have other problems because, for example, we have the curve of the Earth. So we need to dig into the Earth. And then we have other problems about seismic noise. And then, the detection also needs to follow. So the instruments to detect needs to be sensitive enough. And then also there is the problem of size. Since there is all this noise linked to the ground, for example, we have to put the detectors in a very desert area. And there are not very desert places that can be like we can go into the desert, but it's for researchers to be in. It's hard, so we need to search for a place that is big enough. But then there are places that are too crowded. So and also isolated enough. Yeah, so that's what it is. So big enough, isolated enough on Earth, there are not that much where there can be human beings around. So, yeah.
I think you should go to the second part.
Okay. If there's other question, we can then talk after that. So, a reflection about all what we've talked about the universe. And so when we talk about science, usually science gives the question of the how. How are things working? How are things functioning? And what, and the what and the how. But there's another question, there's a more philosophical that we can ask ourselves, is the question of why. Why do such events like black hole fusion exist? And that's a good question. So we have this question that we can ask about our world, about our life, about the universe. What are the events that we see? How do they function? But why are they there? And just if we try to think a bit, on one side we have these massive objects, these objects that are completely overwhelming us, and that we cannot even imagine the distance. And on the other side, there is a small planet called the Earth, and even smaller creatures like us called humans. And we can be puzzled when you put the two into contrast. Like, how comes that there are such big things and us? I don't know if you have ever wondered that. So for me, when I try to study that and consider that, I tried also to think about if there's someone behind all that. And if I imagine a God who is almighty, who is powerful, who is infinite, then I can say, okay, this kind of creation can exist because of its hugeness. I can imagine that there is a God who is huge, who is infinite, because he created this massive object. And he also created me. So he created this infinite universe and me and us. And the question is why? And there in the Bible, in the book of the Bible, people have asked this question of this why question. And I want us to maybe to look at one text in the book of the Bible. The Bible, it's a book of a lot of books. You know, there's a small books inside the big book. This is the Bible. And in one of the book, in the book of Psalms, Psalms are hymns, are songs, tell us about who God is. Here's what we read. When I consider your heavens, the work of your fingers, the moon and the stars, which you have set in place, what is mankind that you are mindful of them? Human beings that you care for them. So the author of this poem is raising his eyes to the sky and he asks himself this question. When I see the sky, when I see the universe, when I see all its content, the moon, the stars, and what is mankind? And maybe this is what you've maybe wondered. If you look at the sky by a clear night and you see the stars, you see the immensity of the sky, and this is a question that we can ask ourselves. Who are we? That in the midst of all that, why would a God mind to take interest in little and fragile creatures like us, besides all these big phenomena, all these big objects? Just to try to imagine, do you know, I've talked about the Milky Way. The Milky Way is our galaxy, so the size of the Milky Way is 100 million light year. So a light year, you know what it is? A light year is not a measure of time, we say year, but it's a distance. It's the distance that the light travels during 1 year, and the speed of light is 300,000 kilometers per second. So imagine you run at 300,000 kilometers per second during 1 year non-stop. You will travel 1 light year, and the universe, the galaxy, our galaxy is 100 million light year. So it's impossible to imagine, but this is to say how immense, how big this is. And even if you go just to the closest star from Earth is Proxima of Centaurus. It's 4 light years, but you have to travel at the speed of light during 4 years to reach that distance, and it's enormous. And even if you consider the stars that exist since millions of years, and our Earth is estimated at 4.5 billion of years, and we live like 80 years or 70 years at most. And why do we exist besides such enormous objects and lasting objects? And this is the contrast between us and the rest of the universe, and it's telling something. And yet, if we continue to read the following of this psalm, here's what it said. You have made them is the humans, a little lower than the angels, and crowned them with glory and honor. You made them rulers over the works of your hands. You put everything under their feet. That's what's extraordinary. God has put us little and fragile as we are, little bit under angels. He crowned us with honor and glory. God is the great God who created black holes which can collide, and He made us but he did not just make us like, okay, I have I have two minutes more, and I just met several human beings. No, he took the time to create us and to place us in a place of honor. I don't know if you have ever played with Lego. I have a 2 years old son, and I like to play with him. He's in his time, his period of Lego, and you know, we can create very big things with Lego. We can create very big cities, buildings, etc. And imagine that you create this kind of big city, but then you also place in this city small characters, and you do not place them like, okay, because we have to fill a bit the city, but you take the time to paint them, you take the time, and we like to do that. We like, when I'm with my son, we like to create these big structures and also to put some characters in it. And God has crowned us. We are not just human beings that wake up and eat and then go to the toilet and then sleep, right? We do things. We are able to have this kind of conference. We have abilities. We are able to relate to each other with deep connection. We are able to create so many beautiful things, just the monuments, Notre Dame, the Tour Eiffel, the Taj Mahal. This is incredible. This is human beings who made that. We are able to create AI, robots. Look at ITER. How can such fragile little creatures like us be able to create such a complex machine and run it? And God has taken interest in us. And if you consider how much is this objects in the universe, the planet, the suns, and us, and the question is and remains, why? Why did he take such an interest? And also, how can we know this God? Can we talk to him? Can we communicate with him? And like us, when we are kids, we like to communicate, to make the little characters, the Lego characters, talk and to communicate with them, even though they are very small. Well, I believe that the answer is yes. And God has communicated with us, and we can see that in a second text from the Bible, which is a letter wrote to a church. And here it says, long ago, at many times and in many ways, God spoke to our fathers by the prophets. But in these days, he has spoken to us by his Son, whom he appointed the heir of all things, through whom he created the world. He is the radiance of the glory of God and the exact imprint of his nature, and he upholds the universe by the word of his power. After making purification for sins, he sat down at the right hand of the Majesty on high, having become as such superior to angels, as the name he has inherited is more excellent than theirs. So God has spoken to us. How? By his Son. And the Son is not anybody. He's the one God has appointed the heir of all things, the one through whom he created the world. And he's the radiance of God's glory. He upholds the whole universe. And God has communicated with us not through a voice coming from the void, not through just something coming, no, through a person. A person who walks, who lived, who talked, who can have a relationship with us. And this Son is Jesus. The God who created the whole universe is also a God who speaks to little creatures like us. And that's something that's amazing me. And through Jesus Christ. And God has always wanted to establish a relationship with us, to communicate with us, because he loves us, because he wants to have a relationship of love with us. And the book of the Bible is a love letter that God has written to us. And he wants us to know him and to connect with him. So this is the why answer God has created us and He wants to communicate us because of His love for us. But there's one problem. God wanted to have a love relationship with us. He wanted to know us. He wanted us to know Him. But the problem is that we cheated on Him. The relationship was meant to be exclusive, to be unique, to be intimate between God and us, between God and you, between God and me. But we loved other things. We loved our houses. We loved our money. We loved our bodies. All things that are good, that God gave us out of His love. But the problem is that we loved these things more than we loved God. We cherished our finances, we cherished our family, we cherished our accomplishments, we cherished our professional position, our investments, our successes more than God. So what is the consequence of all that? Well, imagine you come home after a long day of work, you just want to see your wife and kids, or your husband and kids, and you walk into your bedroom and you see your wife with another man, or you see your husband with another woman. What would you do? Well, you would be very angry and sad. And this is how God reacted. He was angry because we cheated on Him. Like lovers, a lover cheats on his spouse, if a lover cheats on his spouse. And the consequence is that we were separated from Him. He told us to go out of His house. And this is the bad news. We are separated from God, the God of the universe, because of our decision to prefer other things than Him. And the ultimate ending of all that is one of the common, our common destiny, which is death. We are going to die. And death is the ultimate consequence of our decision to love other things more than God. And after death, some people say there's nothing after death, but I don't think so. There's something, and the Bible tells us there's a life after death. But if we did not believe in God, if we reject God, the life after death, I'm sorry to say that, is not a life on earth, another life on earth. It's hell. It's a life separated forever with God. A life of regrets, of bitterness, of suffering, and forever. Not 10 years, not 50 years, not 200 years, forever. But here's the wonderful news. God is a righteous God, and He wants to make things right. And if we face this kind of situation, if we face someone that's cheating on us, we want things to be made right. And God wants that. And this is what we are made for. We are craving for justice. When there's injustice, this is touching us. And God wants to make things right. And He has made His justice fall. There's a consequence of our disobedience. Someone had to die. And He made His justice fall on Jesus Christ, on His Son. What? And yes, on His beloved Son, on the heir of all His creation, on the one who is in print of His glory. And why? Again, this question, because He loves us so much. Because He loved us so much that God was willing to kill His own Son at our place so that we can be reconciled. And this is the heart of Christian faith. We call ourselves Christian evangelical. Sadly, nowadays evangelical has a bad connotation, but it comes from a Greek word which means good news. And the good news, it's good and it's a news and it ought to be shared. If you've experienced like a wonderful thing, a wonderful holiday, or you've tasted the finest food at a restaurant, what do you do on Monday morning when you meet your colleagues? Well, you want to share it because you've experienced something wonderful. And this is what we do. as Christians, we want to share something. We've met someone, we had a relationship with someone that changed everything in our lives, and we want to share it. And I want to share it with you tonight, this experience. Another question is, what do we do with all that? We had a lot of information tonight about for our brain, for general culture, and also information about that can concern our life, that can concern our death, our souls, our destiny, our life purposes. And God has created us, and He has spoken to us through a man. And He is the only one, this man is the only one who is like us, a human being who can understand us perfectly. He was tempted, He cried, He laughed, He got angry, and Jesus had all the human experience. And in the same time, He said, I am the way, the truth, and the life. Not a way, not a truth among others, but the way. So He is the one who claimed to be the only way toward God. And this is making Christianity so unique. A lot of religion expect us to come up toward God by our prayers, by our sacrifice, by our rituals. But Christianity is the only religion talking about a God who created everything, who is so glorious, and who stepped down toward us. He stepped down from His throne. He became a human being. He became even a fragile little baby in our world to communicate with us, to offer us life. And He's the only one who could do that. We could not reach Him, so He reached us. Because if someone has cheated on you, you are the only one who is able, who has the power to forgive him or her, to restore your relationship. So that's why God was the only one who could came to us and offer us forgiveness. So my question is, would you consider this God? Would you try to know this Jesus? Maybe we can just have maybe 30 seconds of silence just to think about all we heard and think about this question. Okay, so we are coming to the end of this conference, and I hope that you learn things. If you want, tomorrow we are having a celebration in this very room, a Sunday service that starts at 10:15 a.m. So if you're interested, you are absolutely welcome. And we are going to talk about God. We're going to read the Bible. We're going to sing some songs, and we can discover, and you can discover a bit more about this Jesus. So if you would like, if you're ready to wake up a bit earlier, you can come here in this place at 10:15 tomorrow, and we will be happy to welcome you. And thank you. That's all for me.
So thank you very much, Victor. Very interesting, and he'll be hanging around if you want to ask him questions. I just have one more announcement. So 1 week from tomorrow, what we call Easter Sunday, and we're having a special day of celebrations here. And so I'm going to put it on a slide with a little bit bigger letters to be able to see what's happening. So we'll have a service here at 10:15 where we will sing some songs about Easter. there's some children preparing an orchestra, and we'll be singing together. And then everyone will bring a dish. We can eat together, have a lunch here together. And then in the afternoon, there's going to be an escape game. Do you know what an escape game is? There's different challenges. You have to figure things out, to decipher special messages, have some logical games. And this escape game will be around the Easter story. Okay, if you don't know the Easter story, you have to come and learn about the Easter story. And at the same time and after, there'll be some games outside. There's basketball, there's ping pong, there's baby-foot, and so we'll have a nice afternoon together. But I would like you to sign up for that. So you have to send me a message, so just we know how many people will be here. It helps us to prepare for the games. Okay, thank you again, Victor, and please enjoy the snack. I forgot to mention the Easter egg hunt for the children.